So this video is about power sets, but before that, let's do a little bit of a warm-up kind of thing. So let's consider this statement. X is a perfect square. So what does this mean? Well, this means that x could be 4 or it could be 9 and so on and so forth, because as you can see, those are indeed perfect squares. Now the problem is, how do we express this statement in terms of logic? Well, I'll show you one really easy way to do it, and this comes with the help of sets. So if x is a perfect square, then definitely x should be part of the set which consists of all perfect squares, right? Because if x is a perfect square, then it's guaranteed that x is inside this set. Therefore, if x is inside this set, then it is a perfect square. So those essentially communicate the same idea. Alright, so how do we construct this set? We can't just put a set there and say all perfect squares. We need to formalize things and express these idea in terms of logic and mathematical statements, because this part over here is still English. Alright, so all perfect squares. How do we construct that set? Well, what if we write n squared over here and we make it so that n squared should satisfy n being part of the natural numbers? And the natural numbers goes from 1, 2, 3, 4, 5, and so on. So if that must be satisfied, then n squared should be 1 squared, 2 squared, 3 squared, and so on and so forth. So this is the set which contains 1 squared, 2 squared, 3 squared, and so on and so forth, i.e. it is the set which contains all perfect squares. And well, if x is in this set, that means that x is a perfect square, so these two statements communicate the same idea. Except this one is more preferred because it contains logical symbols and set theory which we have an understanding of and we can easily manipulate. It turns out there's a different way to express this idea in terms of logical statements as well. And if we're able to construct whatever this statement is, then since they communicate the same idea, that means that this statement should be equivalent to this statement. So how do we construct this statement? Well, consider the existence of a number n such that that number is part of the natural numbers and that it satisfies the following proposition, which I am going to cover in brackets. And this proposition is n squared should equal x. Well, how does this relate to x being a perfect square? Well, if x is a perfect square, then x is equal to n squared. That's just the definition of a perfect square. And n is equal to something from the natural numbers. And since this is what it means for x to be a perfect square, if this condition is satisfied, then x is a perfect square. How do we satisfy this condition? Well, how do we satisfy it? Well, we just have to show that there exists an n which satisfies this condition over here. And well, if it satisfies this condition, then this condition is true, and if this condition is true, then x is a perfect square. Meanwhile, if there does not exist a number n which satisfies this condition, then it's impossible for this statement to be true because there doesn't exist a number n which can satisfy this. If it's impossible for this statement to be true, then x is not a perfect square. Therefore, this whole thing over here just translates to this. If there exists a number n, which is part of the natural numbers, that satisfies this condition, then x is indeed a perfect square. And I know this is a bit more difficult to understand than this guy over here, so let's use an example. Say that x is equal to 4. So let me just erase this and put the number 4 there. So we want to show that x is a perfect square. So if we want to show that the number 4 is a perfect square, then we have to make this statement true. But if we want to make this statement true, it's equivalent to making this statement true, because we have determined that these two are equivalent. So, is this statement true? Well, yeah. There does exist a number n which satisfies this condition, and that is the number 2. N equals to 2, and 2 squared is equal to 4, and 2 is indeed part of the natural numbers, so everything is satisfied. Well, what if we have something that's not a perfect square, say the number 3? Well, what are the numbers that satisfy this condition? Well, it's square root of 3 and negative square root of 3. But they're not part of the natural numbers, they're part of the irrational numbers, which means we can't say that this is true. So this statement is false in the case when x is equal to 3. Therefore, since this is false, this should also be false. And x is, well, it's not a perfect square because it doesn't satisfy this condition here. The implication here is that this statement and this statement are equivalent to one another because they communicate the same idea, that x is a perfect square. The fact that x is a perfect square precisely depends on these logical statements to be true. And the equivalence between these two statements is important because one of them involves set theory and the other one involves, well, quantifiers. And this equivalence acts as a bridge between set theory and quantifiers. So it is pretty important and we will see it a lot in the future. Now on to the topic of power sets. Well, in short, a power set creates a set from subsets. What do I mean by that? Well, let's illustrate this with an example. So let's take the power set of A, and A over here, mind you, should be a set. And let's use an example. Maybe A is the set containing 1, 2, and 3. So the power set of A, it creates a set from subsets. And what subsets? Well, subsets of A. So the power set of A is a set which consists of the subsets of A. What are the subsets of A? Well, let's draw a Venn diagram because maybe that will help. Well, I can definitely put the empty set here. It's definitely inside of the set A. So I can just put the empty set down here. I can also make a set which just goes all around 1. So this is the set that consists of the number 1. And I can do the same for everything else as well. So I can draw the set consisting of 3 only and the set consisting of 2 only. And I can also join 1 and 3 together. That's also a valid subset. Everything is still contained within A. So I can write 1, 3 there. And I can also write 1, 2, and I can also write 1, 3. And finally, there's one more subset that we can create. And this is the subset which is actually equivalent to the set A itself, because A is a subset of itself by convention or by definition. So let's just write A here because we're running out of space. So that's it. This is the power set of A. It's a set which inside of itself consists of sets too. So these are not numbers. This is not the number 1. This is not the number 3. This is the set containing 1 and the set containing 3. And this concept of a power set is important in topology. But what are we concerned about in the study of logic is if we have an object X and we have determined that it is inside of the power set of A, how do we express this idea in terms of logical statements? Well, everything inside of here is a subset of A. In other words, if we have the power set of, say, a set S, a set containing mathematical objects which satisfy being a subset of S. Hence, if X is inside of P of A, then the only way that this is possible is if X is some subset of A, because everything inside of here is a subset of A. So if X is inside of it, then X better be a subset of A. And we already know how to convert set theory into logical statements. We've done that in the previous videos. This is equivalent to showing that for all mathematical objects y, if y is in x, then this would mean that y is also in A. And that's pretty much it. So that's it. That's another example of a conversion from set theory into the language of quantifiers. So let's try to deal with a more complicated example. So let's say we want to express this idea in terms of logical statements. How do we do that? Well, this shouldn't be too hard, because if x is inside the power set of A intersect B, then x is a subset of A intersect B. And we already know how to express that in terms of logical statements. This means that for all y, if y is in x, then y is in A intersect B. And this guy over here, we've already seen how to translate that in terms of logical statements in previous videos. This is equivalent to saying y is in A and, hold on, that's or, and y is in B. What if we have instead x is an element of the power set of A intersect the power set of B? Well, let's just start. If x is in the intersection between P of A and P of B, this must mean that x is inside of P of A and it is also inside of P of B. And this guy over here, we've already translated before, right here. So we just have to copy and paste. So this just translates to, for all values of y, if y is in x, then y is in A. And you can see that this is exactly the same. We just have to change the A to a B. So for all values of y, and we can also use the same variable, no problems there. Y is in B. And that's it. This is how you translate this thing at the top into logical statements. Now it turns out that this thing over here is equivalent to this thing over here, meaning that this thing over here is equivalent to this thing over here. So how do we show that this guy and this guy is equivalent? Well, we just have to use our pre-existing knowledge. Let's start from this guy and slowly modify things and work our way towards this thing over here. Alright, so what can we do? First, let's simplify the if-then statement. Remember the if-then statement. If A, then B is equivalent to not A or B. This is something we've covered in previous videos. So in this case, this thing over here is A, and this thing over here is B. So not A means just Y is not a part of X. And we have the OR statement, OR, and then we also have B, which is just Y is an element of A, and Y is an element of B. Now we're going to use a lemma here. And the lemma is if we have a proposition A, or, and we have brackets B and C, then this is equivalent to A or B and A or C, bracket, bracket. And to prove this lemma, it's not too hard. You just have to make a truth table, and I'll just leave you to fill in the details. Basically, this lemma allows us to simplify what we have at the top over here. And by the lemma, we can just instantly write this bracket and this bracket. And this has the same structure as not A or B. So this is not A or B. So we can just convert that back into the if-then statement. So if y is an element of x, then y is an element of a. And this one can also be converted back. And I think it was the last video where we proved a lemma saying that we can distribute a quantifier as long as there's an and sign between two statements. So we can just distribute the quantifier and just do this, and we're done actually. So as you can see, this thing over here, it should be equal to whatever we have over here. And yeah, that seems just about right. We do end up with equivalent statements once we were able to modify things. Therefore, we have proved that this statement over here about power sets is equivalent to this statement over here.